Good afternoon, ladies and gentlemen. Welcome. We will start today with unsupervised learning. Not like this image may represent, it could be a self-supervised learning, it could be, I'm too early, sorry. It could be reinforcement learning. Thilo will talk about this next week. And in 2 weeks, we will recap the expectation maximization algorithm. I think it's time for that, and we will also, as promised, solve together some riddles, some questions, multiple choice questions mainly, which goes over the task or over the topics that I presented. Okay, yeah, what is unsupervised learning? Here you see the full classification actually of machine learning. We can divide it into 3 big topics: supervised learning, where we have labeled data; reinforcement learning next week; and today we look at unsupervised learning, mainly clustering. We looked at the technology last week, dimensionality reduction, where we were able actually to recover such manifolds. That's a representation of a 2-dimensional manifold, which doesn't need to be a plane. It could be any curved connected region in a high-dimensional space, and we found methods how we can reduce this to any dimensionality using PCA or another technology called TSLE. Today, we look at different technologies for clustering. Clustering means detecting groups in data. It's really recovering or discovering things that were not known before. And I think most of the data in the world is actually unlabeled data. So this topic is quite important. We can divide clustering algorithms into different classes. One way to divide those algorithms would be like this: hierarchical clustering. There we can start from bottom up. This would be called agglomerative, so like collecting things together to bigger groups. Or we can go top down and consider all the data in these high-dimensional spaces. First of all, one big heap of data, which is just one big cluster, and we could start dividing these into smaller parts. This is called divisive clustering, and there's also a way to do this in a hierarchical way, and this is called this divisible spanning tree clustering. Then partitional clustering, it's a very famous representative here. The K-means clustering method means actually that we try to find groups, not just by a hierarchical step-by-step method where you can see, okay, this is iteration 1, 2, 3 or so, but to try to group these data in a similar way that actually a Gaussian mixture model would do it. Then we look at different things, how we would evaluate a clustering. That's quite difficult because we don't have true labels. So the question is, what is a good clustering? How do we measure actually what a good clustering is? It's quite a difficult question. And then we look at the version of a density-based clustering, which is again a different approach how you could do it. It's called dB-scan, density-based clustering, which is a very powerful method to group high-dimensional data based on the density of this distribution. What we look at in 2 weeks, on the 21st of May, will be first actually model-based clustering, and the most important representative there is actually clustering using Gaussian mixture models, where we also have hidden latent variables, which we want to estimate out of the data. Those labels could be hidden and remain hidden, but they assign actually to each data point the membership to a given cluster. There's a way to, we'll see soft clustering, because we can assign a probability that such a data point, a member, belongs to any cluster K. And then there are other methods which just assign this is in cluster 1 and 2, and no probability given. Okay, so clustering in short, I would say is finding groups in data, whatever a group is. And the problem we could formulate like this. Given n data points, we want to separate these into n clusters. N is the number of data points, k the number of clusters. This k can be given, or it can be found itself, not by the algorithm. Delta is a given partition of the data points in several clusters, and we have just named, okay, we want to have k clusters, or the output may be a k clusters. We can always base, actually, or justify a clustering method, and we can assign it to a given loss function. So to a certain clustering algorithm, there's always also a corresponding loss function, which is then minimized. This is another way to do it. We could always actually generate new clustering algorithms by defining these loss functions and then minimizing those. There's a typical approach in machine learning. Another way to read the taxonomy of clustering would be part clustering, as I mentioned. So we just assign to each data point really a membership. You belong to cluster 5, you belong to cluster 4. Soft clustering means actually we express this membership by a probability, so that the probability of this data point is 60% that it is in cluster 3 and 40% in cluster 5, for example. So it's kind of degree of membership. And this is it's a softer way to do it. It's not that we have hard edges, but we can still discriminate or say, okay, how accurate do we want, or how sure do I want to be that this data point is in a given cluster? Yeah, if you look at these data, how would you cluster these images? And the goal of this transparency is to show actually that there are different ways to do it. Huh? We could actually say, okay, let's make 3 groups. We could put insects together, we could spiders together, which are not insects, and we could put invertebrate together. It's a valid clustering. It's a taxonomy of animals, for example. We could also say, okay, all animals that have legs, we put together in a big cluster, and all others in another cluster. So we would have 2 clusters. Then we could cluster different things. We could say, oh, let's put together all animals that have wings and all that don't have wings. It's also valid. So it means, okay, we have to define what means close together. It's again actually a definition of similarity, what means actually belonging to one cluster. And this is what we look at today. Yeah? We could define similarities using this picture in very different ways. Why clustering is very powerful is now actually in computational biology or bioinformatics. That you analyze nowadays gene sequences, and you can do this quite cheap and fast. And this is here, it's done using yeast cells, so Hefezellen in German, yeast cells. And there are many, many different kinds of yeast cells. But if you want to make kind of a evolutionary tree out of that, you can analyze the gene sequences and just let them, as given data, group it together using a clustering algorithm. And what turns out is kind of I would say a Darwinism tree, like a development tree of these animals. We see what is the ancestor, what are the children, and the children of the children, and so on. Who is related very close to the other? This could be a subcluster. We could also say this is a big cluster. So this is now an example of a way to agglomerative clustering to a hierarchical clustering, because we could stop here and say there are mainly 2 groups. We could also stop here and say, no, actually, I think we should make 3 groups out of it, because they're still different. If we make a cut here, we would say, okay, there are probably 9 groups which we have to differentiate. So it depends on us how fine we do want to have the clustering at the end. Typical example of a hierarchical clustering. There's even Python code for that, so whoever has gene material at home or something data at home, you can once try it with your family genes to make actually your ancestral tree out of it. Probably it's too early. Okay. Another way to look at clustering is also actually from, let's say, data reduction size. actually vector quantization or quantization of data into a dictionary is already clustering. It's actually looking for centroids of the data when we assign similar things to it. So we could reduce actually the colors of an image to only 64 colors. And it's not smart to do, say, let's say we have 16 bits of color, then we just divide it in a linear scale and say, let's make now 6 bits of color. This is not a smart way. Smartest way is to look which colors are really represented most in the image, and then assign similar pixels to this kind of dictionary of the image. And this is what you will do in the exercises, an image quantization. And it's amazing how you can reduce actually an image if you have the right dictionary to it. Where you say, these are the dominant colors in that image, and I assign similar colors to the centers of colors. So I have a certain palette of colors which represents the image, and then I assign all other pixels to this palette. Yeah, not only for images, for any message, for any data, we can actually concentrate the data, we can zip the data together. And one very funny example is this one here. Probably you've seen this from David Kriesel. Xerox is this famous company which actually invented the mouse and almost the computer, I would say, but it's famous for these copying machines. The copy machines, they use a kind of compression algorithm which is based on image quantization. So similar patterns are assigned to one member of that dictionary, which returns often, like a part of a K or an E and so on. And this is recognized as an E, and then you will only store, okay, it's an E. It's a member of an E. And this, of course, saves a lot of data, but the problem was actually that the data was recognized wrongly there, because actually this compression was quite high. And if you scanned an architectural map with measures inside, distance measures, actually, they were flipped. The data was flipped, and you would build a different house. So it's very amazing to look at. If you want to have time in the train or so, have a look at this video. It's really amazing, and it's also amazing how this Xerox company reacted to this response, because it was a very big company. This is a very nice image. Like, yeah, if Darwin had seen that, I think he would have been happy, because this is kind of the truth, or this is the proof that his theory is maybe right, and we can reconstruct it out of the gene data itself, blindly, just analyzing these gene sequences. We can define similarities. How many, for example, gene flips were necessary? How many crossings of chromosomes were necessary to make actually a link between these and these? So the later actually, or the more distance these clusters are, the more mutations were actually necessary to generate one species out of another. And this is actually a similarity measuring. For example, the number of mutations necessary to come from one sequence to another, like one sentence to another. How many letters do I have to flip so that I get from one sentence to the other? It's a similarity measure. The difference to clustering is actually, yeah, the main difference is actually classification is still supervised. Classification is supervised, clustering is unsupervised. The cost function actually in classification is the expected error, and here we can define really many different loss functions, and therefore there are also different clustering algorithms. What is important here, the generalization, for classification it's mainly the performance on new data. Here it is mainly the performance on the given data. So this takes quite a time to find these clusters, and the performance to do that clustering is actually what matters. K is sometimes known. Here in clustering it's maybe unknown. There are other algorithms where we can specify K. The goal here is prediction. I would call this exploration, because we don't know actually what the structure of this data is. That's the goal, exploration. We want to find out, are there correlations inside? Can we group data together to to build actually similar groups with similar properties. This field is maybe mature, and I think there are still new algorithms designed here for clustering for unsupervised learning in general. Okay. We call parametric clustering when K is known, and non-parametric when K is determined out of the data itself. And there are some criteria which can determine an optimum K, and we will also have a look at those. What is the best K? It's like a hyperparameter that we have to select. What is the best number of clusters? And it's not always that easy to say it's the best one. Sometimes if the data is quite overlapping in high dimensions, there can be different solutions, or the minimum can be quite flat. Okay, hierarchical clustering seeks to build a hierarchy of clusters. We'll just see that once. And one subgroup is agglomerative, where we start actually from the point of view that each data point at the beginning forms a cluster. And probably you remember the film Terminator, I don't know which number, but this metal Terminator which melts them, and these drops getting together and building bigger drops and bigger drops and bigger drops. That's agglomerative clustering. So you'll never forget it. Just agglomerative clusters, Terminator 3 or something like that. Huh? Or 2. Okay, so if you ever find this snap of a video, please send it to me, because then I would build it in. It's really a nice picture. Good. Top down, we also see it, but just for completeness, because this is quite difficult. Because it has to do with graph theory. We go from top down, and then we generate a graph, and we take a knife and cut the graph. And where do we cut the graph? Where we have the longest edges. And out of one cluster of clump, we make 2 clumps, and then we continue like that. So this is actually top down, bottom up. This is actually the summary, and we'll first go into the hierarchical clustering. Okay, and look at these two. The difference between a partitional clustering and hierarchical clustering, just shown graphically, is like that. We partition it first actually in a big cluster and 2 small ones. So these things actually are not overlapping. They're not box in box, because if it's box in box, then it's rather such a thing. This is called, we have different iterations, different kind of recursion depth, which are built on each other, and that's a hierarchy of clusters. So we have to decide when we stop the iteration or the recursion, and we can still continue until we get actually one big clump of data if we start top bottom up, or we stop when we end up at each data point if we go from top down. So we have to decide when we stop. There must be a stopping criterion, and this stopping criterion actually determines the optimum K, the number of clusters, and we have to see where this optimum K comes from. It can come from information theory, which says, okay, there should be some measure should be optimum at this point. A traditional dendrogram is like this, that we actually make only a partition at one at a time, one at a step. Yeah? So we would divide this first one in 2 clusters, then 3, 4, and so on. And here a non-traditional dendrogram would do it parallel. So just divide it from 2 into 4. But we mainly look at the traditional hierarchical clustering, agglomerative clustering, this kind of clustering. Then there are other ways to do. Sometimes soft and hard clustering is also called fuzzy. It's a little bit fuzzy. Partial versus complete. Sometimes we only take only part of the data to be clustered. Heterogeneous versus homogeneous. Sometimes clusters must have more or less the same size. We can also force that. Sometimes we can say, no, they are allowed to have very different sizes. Okay. Let's look at hierarchical clustering. And for this, we have to first say, okay, from what criterion do we actually derive a similarity? And similarity, as last week, is related to a distance measure. It can be quite a general distance measure. We just have to find it in terms of a matrix, a real metric. And the metric has 4 axioms, we'll see that again. And together with a distance measure, distance from here to here, and the linkage criterion, we actually have more or less already defined a hierarchical or agglomerative clustering algorithm. And let's see how this works. So we need a metric and a linkage criterion. What is a linkage criterion? A linkage criterion is actually the condition at what point 2 subgroups are fused together into a bigger one. This is called a linkage criterion. And if we start from bottom up, we have to think of, okay, when do we fuse 2 clusters together to form a bigger one? And this is defined by the linkage criterion, together with actually the appropriate metric. And we start actually like this. Every data point at the beginning forms itself a clustering, an hierarchical bottom-up clustering. And the 2 clusters at the beginning, there's just 2 data points, which are not only smallest, closest together, they're fused together. For the 2 data points, this is true. The smallest distance decides which 2 points are fused together. Later, actually, these data points already form clusters with many points inside. Now we have to define what is the distance between 2 clusters. And there are different ways to define that. At the beginning, everything is identical because the distance is just the metric itself. And the closest points are in the first step just fused together, and then from n data points, I have n-1 clusters. And then I start from these n-1 clusters to form n-2 and so on. Okay. Yeah, similarity again is defined by a metric. And a metric is a symmetric thing, it's positive definite. It is only 0 if they are really identical, they sit on each other, and the triangular inequality should hold as force axiom. We will mainly actually use the Euclidean metrics today. It's the L2 metrics, and we have just the Euclidean distance in a general high-dimensional space. This is what defines actually the distance. This is not yet the linkage. Now, together with the linkage, this defines when 2 clusters are fused together. The complete linkage is the criterion when we say, okay, 2 clusters are fused together when the maximum distance here between 2 clusters A and B is minimum. So it's the minimum of this maximum. This is actually called the maximum or the complete linkage criterion. The minimum or single linkage criterion is then 2 clusters are fused together, A and B are fused together, when actually their minimum distance between their members is minimum. I'll just show it in a graph or in a graphics. There's a second linkage criterion, and we can select what we want. And choosing different linkage criteria, given the same distance measure, results in different clusters. And this is also a hyperparameter that we can select. In the grid search, we would say, try all these linkage criteria. Then we will see what happens. And then we have to analyze what a good clustering is or what not. Then we have a mean. So when there's a max and a mean, there should also be a mean. And there's also a median, we will see. A mean or average linkage criterion, which means 2 clusters are linked together and fused together, merged into one, actually, if their mean distance is minimum over all pairs of clusters. So all pairs of clusters are compared, and those which have the minimum mean distance between each other are fused together. Here, those that have the maximum distance, the minimum of all maximum distance, and the minimum of the minimum distances. And this is shown a little bit here. So let's see, this is a cluster A, and these cluster B and C. So using the minimum linkage criteria, we would say, okay, the minimum distance between cluster A and B is this one here. This is the minimum of all minima. So, and this one is closer to the minimum from here to here. So these are first fused together before these two. if you take the complete or the maximum linkage, then we would say, well, calculate the maximum distance from here to here and compare it to the maximum distance from here to here. And then actually we take this one, which is the maximum, the minimum to the maximum. Huh? So this seems to be bigger than this one, then we select this one, which is then closer together. Average linking would actually mean that we say, okay, we make actually here the center of gravity of each cluster and measure just the distances between clusters, between the center of gravities. Huh? These are called also the centroids of these clusters. And then we will merge those together which have the smallest separations of their center of gravities. They are fused then together using an average linkage. Now there's also a word linkage, which is often used because this is more actually a statistical linkage criterion, a probabilistic, we would say. It would say, okay, we want to have those that have the minimum increase in variance between these clusters. It's expressed like this, so we take the distance of the centroids squared over, this is the number of members in cluster A, the number of members in cluster B, and we take actually the geometric average over these. This is the word linkage criterion. And the centroid would be then just, okay, two clusters are fused together, those that have the mean centroid. If this is only one cluster now, B, actually, this is the minimum distance between the centroids. Okay, now, clustering means actually we have to calculate all distance from one data point to all others, which is quite a task. Huh? So we have to fill a bit matrix. If we have n distances, we should fill n minus 1 over 2. This is the number of distances we have to calculate. And if you see, actually, in a later step, actually, we have to calculate with the centroid, for example, which is not a part of the data set. So we have to again calculate new distances. But this is not always necessary. It is sufficient if you have just the distance matrix of all data points to all other. For example, if we only have a distance matrix, now we don't have an image, and that's why probably it's a little bit more difficult to imagine what happens. We just have distances. This is the distance between object 2 and object 1. And at the beginning, in this agglomerative clustering, all data points, all objects form their own cluster. Now, those clusters that have the minimum distance, they are merged together. In this case, it's 1 and 2. Now we have to calculate new distances. Huh? So 1 and 2 has now 2 data points, O1 and O2. They're fused together into 1. And they're, of course, now different distances, because here we have 2 points in that cluster. Huh? So we have a distance from this point and from the other point to all others. That's why actually here, from this new cluster, I have a distance 7 and 5 and 8 and 10 now. Both are still valid. And now the linkage criterion decides which of those two, or how to calculate now actually the real singularity measure between those fused clusters. Huh? If we use single linkage, we would just say we take the minimum. It's the 5, and it's the 8 of that one. If we take the complete, it would be the maximum, the 7 and the 10. If we take the average, we take the average of those two. This is the average. And there are also formulas. You can also look at this, the Lance-Williams formula. It's quite famous. You can really completely, for example, also for a word clustering, for a centroid clustering, you can calculate directly out of the distance matrix what happens at each step of a hierarchical cluster. Only using the distance matrix. We don't need any more actually all coordinates. And the distance matrix is just a number. Even if you are in 15-dimensional spaces, it's still a number. It's a number from this point to this point. So we can just reduce the data size quite a lot. Okay. So the distance matrix actually is the input. Means we have to calculate all distance in this high dimensional space. Let's let's assume it's a Euclidean distance from all points to all other points. And there's already a distance function actually in Python implemented. We can use that one as an input. And at the beginning, we start with an initial clustering. This is actually calligraphic C here, which means this is the clustering at iteration 0, giving actually here n clusters at iteration 0. And then at the beginning, each point is its own cluster, and while the number of clusters is bigger than 1, find 2 clusters which have the smallest distance linkage, now using also this linkage criterion, like the minimum, the maximum, the average linkage, etc., to each other, and merge them into one. So we fuse them together, put them together, like in the distance metric, we just put these actually columns together. And out of one cluster, there is now a list of numbers existing in this new cluster, from which we can again calculate actually the distances to all other clusters. And what is the output? It's a tree, it's a dendrogram. It's a tree, kind of a tree, which shows at which level which clusters are built. Let's have a look at this. In scikit-learn, we can take it actually from cluster, from the class cluster hierarchy, import dendrogram, and here this word linkage. Make blobs is actually an algorithm which helps just to generate n-dimensional blobs in a k-dimensional data space. So it's quite useful if you don't have data at hand to just test some algorithms. You can use, say, let's make k clusters which overlap this size in a 15-dimensional space. And make blobs does this. So we can generate that. And here we just make 12 samples. And then we calculate actually the linkage array. This is already the distance, and then the linkage criterion applied. And using this linkage array, we can draw a dendrogram. And don't forget, we start here from bottom. So we would see that first of all, out of these 12 points, point number 1, or out of these 12 points, point number 1 and 4, they're fused together because they have the smallest linkage in the Ward criterion. The next one would be 6 and 9. They seem to be very close together. And now we can, at each level, we can actually make a cut. And we can stop at that point where we think it makes sense to stop, where we stop the clustering. At this point, it doesn't make sense really to stop, because then we have the whole data chunked in one big cluster. This could already make sense to say, yeah, there are 2 big clusters, 3 clusters, 4, and so on. So we can have any sequence of clusters, and we will see this also. Okay, if we compare these different linkage criteria, at the beginning, actually everything is similar. It's quite the same. The Ward method would fuse the closest together. The group average would also fuse the 2 closest together. The maximum would fuse the 2 closest together. The minimum would fuse the closest together. But then, at some point, it starts to differ. Still that. And now the Ward criterion would hierarchically fuse those 3 together, generate the minimum variance within this cluster. The group average does the same. Now what does the maximum clustering do? Same. But the minimum takes actually those which have the biggest distance here. Together. The minimum of the biggest distance. And then Ward would fuse those together. The group average all these. The maximum takes that one, and the minimum would actually only take that 4th point into it. At the end, there must be always one big cluster, fifths. This is again the same. So clustering depends on this linkage criterion quite sensitively. Has a big influence how this works. And to summarize a little bit, single linkage criterion, which is the minimum linkage, actually tends to generate really long chains in the dendrogram. So quite cluster of clusters of clusters of clusters. Well, to Complete linkage actually makes more compact clusters. This is just a qualitative remark here. And what we also see is actually that linkage algorithms like these agglomerative hierarchical clusters, they are very vulnerable to outliers. Since we use actually the L2 norm, the Euclidean norm, you know, these distances come quite, they have quite a big influence, especially if we take actually a maximum linkage, and then something is always far away. We will see that the single linkage criterion can also formulate it in a divisive clustering algorithm. So we can turn actually the direction top-down and bottom-up and top-down using the single linkage criterion. And this will be actually the construction of a minimum spanning tree, generation of a graph which connects all the data points together such that the distances between these data points all over summed up are minimum. So we generate actually a graph of the data with links together from one data point to another, such that actually the sum of all edges is minimum. That's a minimum spanning tree in this graph. Yeah. The advantage, probably it's also at the same point a disadvantage actually, we do not decide how many clusters we want. We can do it later, we can look at the data and say, yeah, that's more or less what I want. And as a summary also, given different linkage criteria, there are different ways to generate different trees out of the same distance matrix, just using different linkage criteria. Okay. The single linkage criterion of an MST. Now we come to this minimum spanning tree. When we now try to formulate actually this agglomerative cluster, which works from bottom up, from top down, we will actually do this actually using a construction of a graph, which is called a minimum spanning tree. And this would be the distances between these points, and we construct the tree such that the sum of all the length of these edges is minimum. This is called a minimum spanning tree. This would be now a big one cluster, all data point in only one cluster. And now the first step is actually look for the biggest edge, the largest edge, and we cut it in two. The largest edge here we have probably a 9, and we cut it in two, and then we have two clusters. This is the minimum spanning tree of all data points. And the maximum would be an 8, so we have to decide whether we cut here or here. So we have 2. If we cut here, we have a cluster here and another cluster here. And then we will continue into the next one. The next one would be this one, and we cut it here. And the other one would be probably the 8, and we cut it here. So we go from top down. First of all, construction actually this minimum spanning tree. And then cutting just the biggest edges, and we can do this n times or k times to generate k clusters. And then we can stop. That's actually the way a divisive clustering algorithm works, and it turns out that the clusters generated by this method are the same like using the single linkage criterion from bottom up. They generate the same types of clusters. So they're equivalent, because they actually minimize the same cost functions, and then they must be similar. That's here actually shown. Yeah. And I mean, even if the data is very high dimensional, the distance is just a scalar, it's just a number. And we have, of course, n points connecting the other ones, and there's always one single minimum spanning tree that we can cut in half to generate two clusters. Okay. I suggest that we make 5 minutes break, and then we start with a very nice algorithm k-means, and you see many ways to implement k-means again. So like there are many linkage criteria in a hierarchical clustering, there are also for the k-means different ways to in detail implement this k-means algorithm. Yeah. 10 minutes break. Do you agree? Okay, then we make 10 minutes break.